Okay, so let's do these conservation of energy problems. So the first step is to choose an arbitrary zero. So for me, I'm going to make this the zero, which means that right here, 1 meter up, and the reason I know it's 1 meter is that this string has a radius of 1 meter. 1 meter up, this ball has mgh as well as 1/2 mv squared. And this ball just has mgh2 energy here, meaning there is potential energy here, there is potential energy here, and there's also kinetic energy. And the total energies at each point will be equal. Okay, so energy here equals energy there. The total energy of the system at the initial position, energy here, is going to be mgh, or 1 kilogram times 10 meters per second squared times 2 meters. 20 joules of energy. Since energy is conserved in this system, because there are no non-conservative, aka friction and air resistance forces acting on the system, as far as I know, there are 20 joules of energy when the ball is at the bottom of its swing, or energy there. Neglecting air resistance, so here it just tells me there are no non-conservative forces acting. How fast is the ball going when it reaches the bottom? Well, if energy here equals energy there, then I know that the potential energy, gravitational potential energy at the top, is equal to the gravitational potential energy at the bottom plus the kinetic energy. So I have gravitational potential energy here equal to gravitational potential energy there plus kinetic energy there. Or mgh2 equals mgh1 plus 1/2 m v squared. mgh2, if we factor out an m, equals gh1 plus 1/2 v squared. So because the masses are being multiplied on both sides, I can simplify even more, and I can say gh2 equals gh1 plus 1/2 v squared, or v squared equals 2 times the quantity, gh2 minus gh1. Square rooting both sides, v equals the square root of 2 gh2 minus gh1, where g is 10 meters per second squared, h2 is 2 meters, h1 is 1 meter, or v equals the square root of 20 meters squared per second squared. V equals 4.47 meters per second. Okay, so this was just done by setting the energy here equal to energy there and figuring out what type of energy exists at each point. Because the ball is being held still at the top, there only exists gravitational potential energy at here, and at the bottom of the swing, the ball is still some distance away from the earth, so it still has gravitational potential energy, but now it's swinging, so there's also kinetic. Okay, question D says, now there are non-conservative forces, or there must be, because the energy is not conserved from here to there. Energy has not been conserved from here to there, which means there must be a non-conservative force like friction or air resistance acting on the system. So I know that the potential energy there was equal to 10 joules, because 1 kilogram times 10 meters per second squared times 1 meter equals 10. And if 20 joules have to be present, then there must be another 10 joules of kinetic energy. And that is verified from the equation above, where we use that 10 joules of kinetic energy to solve for the velocity. But now this problem says there must be a non-conservative force acting on the system, and instead of moving at a speed of 4.47 meters per second, the ball is actually moving at only 3 meters per second. So the kinetic energy there is 1/2 times m times 3 meters per second squared, or 4.5 joules of Ke. There was supposed to be 10 joules of Ke at the bottom of the swing. There was only 4.5 joules, so the non-conservative force, like friction or air resistance, was responsible for the loss of 5.5 joules of energy from the system. That's equivalent to the work done by that non-conservative force, because remember that work is a measure of how we consider how energy is changed of a system. So that means that the frictional force did 5.5 joules of work, and there was 5.5 joules dissipated or removed from the system by friction. Once the ball is completely stopped in the there position, how much work would you have to do to move the ball back up to the original height? Well, if the ball is stopped in the there position, then there's only gravitational potential energy. And how much? Well, there's only 10 joules because it's only 1 meter away from the Earth. So in order for me to move it to the here position, where there are 20 joules of potential energy because it is 2 meters away from the Earth, I must have to do 10 joules of work.